In this class, we will introduce perhaps the most useful of all tests available to evaluate differences between groups using mean scores, the analysis of variance, or ANOVA. The t-test allows us to evaluate hypotheses concerning one or two means. But what happens when our research design is more complicated? Basically, the t-test cannot be used to evaluate hypotheses concerning more than two means or that involve more than one independent variable. For example, we might expand the basic study we've studied in previous classes by randomly assigning our sample of depressed adults to our experimental treatment, to a standard treatment already available in the community, and to a no treatment control group. Thus, in this study, our independent variable would have three levels. Although the t-test is limited to designs in which the independent variable has only two levels, analysis of variance can be used to evaluate hypotheses in which the independent variable has two or more levels. In another example, we might start with the study we just described, in which participants are randomly assigned to experimental treatment, standard treatment, and no treatment control, and then expand the study by adding an additional independent variable such as gender, ethnicity, or age. Thus, this study would have two independent variables or even more. Analysis of variance can be used to evaluate hypotheses concerning means for these designs as well. Designs we call factorial designs involving two or more independent variables. Analysis of variance is sometimes called the F-test because hypotheses are evaluated using a different sampling distribution called the F distribution. As we discussed the F distribution in this slide, please refer to Figure 10.2 of Chapter 10 of SPATS, which is on page 232 of the 8th edition. The F distribution is very different from the T distribution in a number of important ways. First, it is a positively skewed distribution that becomes somewhat more symmetrical in shape as degrees of freedom increase. The range of the F distribution is 0 to positive infinity. This difference is because the F is a sampling distribution of sample variances, and because the variance is based on squared values, there are no negative values in the F distribution. Also, because there are no negative values, we are not able to test two-tailed hypotheses. Thus, analysis of variance is a non-directional test. Although T and F differ, the F distribution also shares some properties with T. Referring to the figure in SPATS text, notice that just like the T, the F distribution changes shape as degrees of freedom increase. In addition, the critical value will function in the F test just like in the T test, in that it will divide the distribution into regions of acceptance and rejection, and when alpha is equal to 0.05, the area under the curve that falls beyond the critical value all the way to positive infinity is 0.05. Before going to the next slide, see if you can answer this question. Because the F distribution changes shape as degrees of freedom changes, what will happen to the critical value in the F distribution when the sample size, or N, increases? To answer this question, you'll want to turn to the F table in the appendices in SPATS text. From the F table, we learn that the critical value decreases in value as N increases, just like the T distribution. To see this, we need an introduction to the F table. To use the F table, we need to know two pieces of information: degrees of freedom associated with the numerator, which is reported across the columns of the table, and degrees of freedom associated with the denominator, which is reported in the rows of the F table. Degrees of freedom numerator depends on the number of levels of the independent variable and is computed as k minus 1, or the number of levels of the independent variable minus 1. If there are two groups or two levels to the independent variable, then there will be one degree of freedom in the numerator. If there are three groups, then the degrees of freedom numerator will equal k minus 1, or 3 minus 1 equal to 2. Degrees of freedom denominator depends on the size of the sample. We'll discuss how this is computed in more detail later in the class, but as the sample size increases, degrees of freedom denominator also increases. To answer our question about what happens to the critical value as n increases, just locate a column. Let's use the first column where degrees of freedom numerator is equal to 1. And then watch what happens to the critical value as degrees of freedom in the rows, or n, increases. Notice that when the degrees of freedom denominator is 10, our critical value is 4.96. But when the degrees of freedom denominator equals 40, our critical value is 4.08. Now notice what happens to the critical value when the numbers of the levels of the independent variable increase, or we add more groups to our study. If we follow the critical value across the columns for degrees of freedom equal to 40, we see that the critical value goes down. Thus, if we had 6 groups in the study, our degrees of freedom numerator would be k minus 1, or 5, and the critical value would be 2.45.